be the first of two videos on 3-3 polynomial identities. This page 146, Explore and Reason, this is something that you were assigned to do in savasrealize.com. So I am going to go over the answers now to that. So please make sure before you continue with this video that you have gone through and attempted those questions. Again, I'm grading it on effort, not that you get the correct answer, so it is in your best interest to go through and try it first. This is the same as page 69 in your student companion as well. And I do have our essential question here. How can you use polynomial identities to rewrite expressions efficiently? So this arrangement here, and this is going to come up actually in the second video, this is called Pascal's triangle. It's where every number is equal to the sum of the two numbers diagonally above it. And it gives you this triangle. It has ones on the outside and then other numbers on the inside. And then we have these solutions here. So part A is doing the next 3 rows. Part B tells you what's going on. It says the numbers 1 from the left, they're going to move up by 1. There's a few other conclusions you can make for that as well. And then part C, this formula, if you actually look at the sum, is 2 to the n power. So it's always going to add up depending on what row you're in, and it's going to be the value of the row. But keep in mind that we start at row 0 on the very top and not at row 1. Okay, so then we have identity. Identity is a mathematical statement that equates two polynomial expressions. You can see 3 here. There is a 4th one down below, difference of cubes. That's actually sum of cubes. So difference of squares, that's when you have two perfect squares being subtracted. They factor into a plus b and a minus b, and you see some examples over here on the right-hand side. If you recognize that you have two perfect squares being subtracted, they will factor this way. And on the flip side, if you recognize that you have the same thing in parentheses, but one's plus, one's minus, instead of going through the entire FOIL process, you can actually just square the a and square the b and put a subtraction between them. Square of a sum, that would be a binomial squared. You have that formula here, the a squared plus 2ab plus b squared. So you can do that expansion without going through and actually doing the FOIL. That is something else that we're going to be practicing in this unit. And then we have cubes. So we have difference of cube and sum of cube. These are identical factoring patterns except for the placement of the subtraction sign. So with a difference of cubes, your subtraction is going to go in the small set of parentheses. So you can see that in the little set, the binomial set. With a sum, the subtraction is actually going to be first in the trinomial part, the bigger set of parentheses. So you have an a cubed and a b cubed. You have to recognize what your perfect cubes are. So we have the perfect squares that we went over in class. Your cubes, 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125, 6 cubed is 216, 7 cubed is 343, 8 cubed, 9 cubed, 10 cubed. Of course, 10 cubed is 1,000, 9 cubed is 729, 8 cubed, I can't remember what that is offhand, but that is something that you probably won't have to work with too much. So I would just take a moment and jot down some of these cubes so that you have them. It's a very good idea to be able to recognize what a perfect cube is so you can recognize whether you have a sum or difference of cubes. You have 2 different examples here. Notice for this one, for difference, 8m cubed minus 27, 2m is the cube root of the 8m cubed, and 3 is going to be the cube root of the 27. So notice the 2m is the a and the 3 is the b, and then we're just plugging into the formula. So difference of cube, sum of cube, I would take a moment, pause this video, and copy those down so that you have those to reference whenever you're going through and doing work. Which brings us to example 1. It says, how can you prove the sum of cubes identity, a cubed plus b cubed, is equal to a plus b times a squared minus ab plus b squared? We are going to prove this by FOILing the right-hand side of the parentheses. So we're going to multiply the a by the a squared, by the negative ab, and by the b squared, which gives us a cubed minus a squared b plus ab squared. And then we're going to multiply the b by all three of those things. So that's going to be plus ab, or a squared b, minus ab squared, and then plus b cubed. And then when we go through and combine like terms, I have a minus a squared b and a plus a squared b, a plus ab squared and a minus ab squared, and I end up with a cubed minus b cubed. So that verifies our identity, it proves it, everything checks out, we know that that is correct. Our next two examples are going to be going through and practicing using some of those identities. So we're not actually going to go through and do any more proofs, but we are going to go through and use some of those in some ways that should be helpful for you. So this one, we have part A and a part B. Part A, we have two terms that are being added together, and they are being squared. So this is the square of a sum. Oh, there's no E on the end of sum. Square of a sum. So we want to recognize what or figure out what our A term is. Our A term is what comes first, which is 2x squared. B term is what comes second, which is the y cubed. And then we are going to plug both of those terms in. So the formula is a squared plus 2ab plus b squared. So I have 2x squared squared plus 2 times 2x times y cubed plus my y cubed squared. And then we would go through and simplify. So the 2x squared squared, remember you need to square the number and the variable. So that's going to be 4x to the fourth. If I multiply my three terms together, 2 times 2x squared times y cubed is going to be plus 4x squared y cubed. And then y to the third to the second power, y cubed squared. We multiply exponents. That is going to be y to the sixth. So there's your expansion. Now part B, this one is a little bit different because this is just showing you how you can use the polynomial identities to simplify something like this. This is not something that I think will be extremely useful in the long run, but it does show you an interesting representation from the numbers. So 41 and 39 are both 1 away from the same term. 41 is 40 plus 1. 39 is 40 minus 1. Which means this is a factorization of a plus b, a minus b, which means the original problem was a squared minus b squared. Which means this multiplied together is going to be 40 squared minus 1 squared. Well, 40 squared, that's the same thing as 4 squared, and then you add 2 zeros, so that's 1600 minus 1 is 1599. So it is a neat relationship. It makes it a little bit easier than trying to go through long division for 41 and 39, or going through the longer, not division, multiplication process for 41 times 39. Okay, now we're going to get into some factoring. So this is going to be using our difference of squares and then our sum and difference of cube formulas to go through here. So for part A, both of these terms are squares. You can tell that they're squares because the exponents are even and the numbers are both perfect squares. So this is difference of squares, which I'm going to refer to as DOS. So if you see the DOS shorthand, you'll know what that means. The square root of the first term is 3m squared. The square root of the second term is 5n to the third. Remember, the formula is a plus b, a minus b. So that's going to be 3m squared plus 5m cubed, n cubed, and then 3m squared minus 5n cubed will be my factorization. Part B, with both of these terms, and again, you always want to look for a greatest common factor. I know I kind of glossed over that in part A because there wasn't a greatest common factor, but sometimes you won't actually see the sum or difference of cubes or of squares until you factor something out first. So you want to make sure that you check and see if there's anything you can divide them by. In part B, there is nothing as well, so I have to look at my terms. 216, that does appear on our cube list. 216 is actually 6 cubed, so the cube root of that would be 6. Variables are perfect cubes if their exponents are divisible by 3. So x cubed, I can divide the 3 by 3, so this is a perfect square or a perfect cube. 2 perfect cubes being subtracted, so this is a difference of cubes, and I will refer to that as a dot. So the cube root here is x, the cube root here is 6. The formula is a minus b, and then a squared plus ab plus b squared. Notice that there's no 2 with the ab like there is whenever you have a sum of squares. That's one of the things that makes this different. And also that trinomial, the a squared plus ab plus b squared, should not be able to be factored. It may look like it's going to be factored, but that is usually a trap. You will not be able to factor that. Typically, it gives you an imaginary solution if you were to solve using the quadratic formula. So now I plug in. I have x minus 6, x squared plus 6x plus my 6 squared, which is 36. And you can always check this by going through and remultiplying to make sure that it does add up to what it's supposed to add up to. Okay, and that brings us to part C. These are both perfect cubes, 11 cubed and 5 cubed. And again, this is something that it may not necessarily be easier to work it out the way that we're going to work it out, but I want you to see how this is used. So I do have 2 perfect cubes added together. This is sum of cubes, which we will be calling SOC. So cube root here is 11, cube root here is 5. So it's the same exact formula as I had for difference, except for the subtraction, rather than being in the little set, it's going to be first in the big set. So this is 11 plus 5, and then 11 squared minus 5 times 11 plus 5 squared. So 11 plus 5 is 16. 11 squared is 121, and then minus 55 plus 25. Well, that makes a negative 30. 121 minus 30 is 91. So I guess you could make an argument, is 16 times 91 easier than figuring out 11 cubed and 5 cubed and adding them together? I don't necessarily know, but it does work out the same way. And your 16 times your 91 is going to give you 1456. There is a lot more practice you can do with sum and difference of cubes. Again, this was just kind of an introduction, so you will be seeing this more as we move through the sections. But this is the end of part 1. So please make sure you go through, rewatch the video, see if there's anything that you're not sure of, copy down any formulas that you should commit to memory, and be sure to watch part 2 and reach out to me if you have any questions at all.